For decades, laser weapons lived comfortably inside science fiction novels, glowing on starships and in the hands of heroes who didn't worry about power cables or thermal limits. Today, that fantasy has migrated into defense budgets, engineering labs, and real-world battlefields. The world's biggest militaries aren't dreaming about lasers anymore. They're building them and testing them, and in some cases, destroying drones with them. Over the past 8 years, the United States alone has funneled over $7 billion into directed energy programs. Israel is preparing to field a laser that neutralizes rockets for pocket change. China is rolling out turret-mounted systems sized for ships. Russia claims it can blind satellites from the ground. The age of beam weapons has moved from maybe one day to already happening. And although missiles still roar and radars still sweep the sky, the next generation of weapons is quiet, near-instant, and brutally efficient. This is the new laser arms race. Who's building what actually works, and why every major power wants a slice of the light-speed future. The first naval laser that lives up to the promise. The United States spent decades chasing functional ship-mounted lasers. Most prototypes flickered through weapons tests and quietly disappeared. Then came high-energy laser with integrated optical dazzler and surveillance, the first U.S. Navy laser that didn't just function in a controlled demo, but actually fired from a warship and destroyed a live target. Installed aboard the United States ship Preble, an Arleigh Burke-class destroyer, high-energy laser with integrated optical dazzler and surveillance is essentially the Navy's first real directed energy workhorse. Delivered by Lockheed Martin, the system combines 3 roles in one elegant package: a high-energy beam that physically damages targets, an optical dazzler that blinds enemy sensors, and long-range imaging systems that help track and classify threats. High-energy laser with integrated optical dazzler and surveillance currently fires at 60 kilowatts, but its modular architecture allows upgrades to 120 kilowatts, enough to burn through drones, disable small boats, and potentially threaten short-range missiles. The system replaced the ship's forward phalanx gun, marking a symbolic shift from mechanical fire to precision light. Why ships first? Because ships already generate massive power. They have room for cooling systems. They face the exact kind of high-volume, low-cost threats that lasers excel at. Cheap drones, explosive remote-controlled boats, and persistent surveillance unmanned aerial vehicles. In the Red Sea and Gulf of Aden, U.S. destroyers have been swarmed with these systems. Shooting down a $5,000 drone with a $2 million missile is a losing formula. Shooting it down with a beam of electricity is not. That last part is why admirals are excited. A laser shot costs little more than the electricity needed to fire it. There's no ammo magazine to run dry, no explosive warhead to store, no reload chain to worry about. High-energy laser with integrated optical dazzler and surveillance still isn't fully deployed across the fleet, but it's already become the U.S. Navy's single strongest proof that the laser era isn't coming. It has arrived. When lasers meet fighter jets. If ships are ideal laser platforms, jets are their nightmare opposite. The U.S. Air Force spent years trying to mount a functional laser on an F-15 under a project called Self-Protect High-Energy Laser Demonstrator. The concept was irresistible: a fighter jet firing a beam that slashes incoming missiles out of the sky. From 2016 to 2022, the program progressed well in lab tests. Lockheed Martin produced a 30 to 50 kilowatt laser called Laser Advancements for next-generation compact environments. Northrop Grumman created precision beam controls, and Boeing built the flight pod. All components were delivered. All components worked. None of them ever flew. In 2024, the Air Force officially pulled the plug. The reason wasn't flawed technology. The reason was physics. A fighter jet simply cannot spare the 250 kilowatts of onboard electrical capacity needed to power even a modest laser pod. Nor can it host the substantial cooling systems required. The Self-Protect High-Energy Laser Demonstrator laser could fire on the ground, but in the air, the aircraft itself became the bottleneck. The Air Force tried the same idea on a much larger AC-130 gunship and hit the same thermal wall. The work isn't wasted, though. The data and engineering lessons are feeding directly into 6th-generation aircraft designs. The next flagship fighters, the United States Air Force's next-generation air dominance and the Navy's F/A-XX, are being built from day one with lasers in mind. They'll be designed to produce huge electrical surpluses, host heat dissipation systems, and potentially carry defensive or even anti-satellite laser capability. Airborne lasers aren't dead. They're waiting for aircraft that can handle them. Israel's Iron Beam. Of all nations racing toward laser weapons, Israel is closest to turning prototypes into a nationwide defensive grid. The upcoming Iron Beam, developed by Rafael and Elbit Systems, is a 100 to 150 kilowatt short-range laser designed for Israel's most common threat category: waves of cheap rockets, mortars, and drones fired in large numbers. In testing, Iron Beam burned through real targets: unmanned aerial vehicles, rockets, and even small missiles. It connects directly to the Iron Dome architecture and uses the same radar and command network. But its biggest advantage is cost. A single interceptor missile in the Iron Dome system costs $50,000 to $100,000. A laser shot from Iron Beam? Roughly $2. That cost difference transforms battlefield math. When saturation attacks send dozens of weapons overhead at once, lasers can handle the cheap threats, allowing expensive interceptors to be saved for the targets that actually demand them. Engineers also tuned Iron Beam specifically for Israel's harsh weather: dust storms, heat shimmer, and haze, all sworn enemies of high-energy beams. Full deployment is expected before the end of 2025, with mobile and vehicular variants already in development. Iron Beam is poised to be the world's first operational battlefield-ready laser air defense system. China's rising laser fleet. China's laser roadmap is expanding at startling speed. Their earlier Silent Hunter, a 30-kilowatt truck-mounted fiber laser, already proved itself when Saudi Arabia used it in 2024 to shoot down a hostile drone targeting critical infrastructure. Quiet, mobile, and export-friendly, Silent Hunter became China's global calling card for directed energy systems. But the real shocker arrived in late 2025 when China unveiled a far larger system called LY-1, a ship-mounted rotating turret reportedly capable of 180 to 250 kilowatt. If the numbers are accurate, LY-1 would surpass even the US Navy's high-energy laser, with integrated optical dazzler and surveillance in raw output. The turret features a notably large aperture, suggesting excellent beam quality and long-distance engagement potential. It has appeared on heavy trucks and has even been spotted on a Type 071 amphibious ship. But there's a catch. China has not shown LY-1 firing at real targets. No sea trials, no sustained firing footage, no data on how it handles ocean spray, humidity, or thermal cycling, all critical challenges that sink laser systems fast. It looks powerful, polished, and parade-ready. But until LY-1 proves itself on the open ocean, it remains a visually impressive question mark. Blinding satellites and questionable claims. Russia's laser ambitions are less about drone defense and more about strategic disruption. Its Peresvet system is a truck-mounted blinding laser, reportedly designed to interfere with satellites passing overhead. The system appeared in 2018 and has since been deployed near strategic missile fields to complicate enemy reconnaissance. Russian officials claim it can dazzle satellites at distances over 1,500 kilometers, but as usual, offer no public demonstration or verifiable data. On the tactical side, Russia introduced Zadira, a laser weapon allegedly capable of burning through UAVs at several kilometers. Officials claimed it was used during the Ukraine conflict. Ukrainian officers immediately dismissed it as wartime propaganda, and no confirmed footage has ever emerged. Russia's lasers may exist. They may even work in limited capacity, but the lack of evidence places them firmly in the unproven category. Why lasers are still hard and still worth it. For all the hype, lasers remain brutally difficult to perfect. The science refuses shortcuts. First problem, power. A combat-relevant laser needs 100 kilowatts or more. Generating that level of power continuously is simple on a ship, impossible on a fighter jet, and expensive on mobile ground vehicles. Second problem, heat. High-energy beams generate enormous thermal loads. If optics overheat, the beam weakens or destroys itself. Cooling is often the real engineering bottleneck. Third problem, environment. Rain, fog, dust, salt spray, humidity, smoke. Every one of these can scatter or weaken a beam. Even Israel's iron beam had to be specially adapted for its desert atmosphere. Fourth problem, durability. A single dirty lens can reduce a laser's output dramatically. Warships do not have the luxury of gently cleaning optics in the middle of a missile attack. Yet militaries care deeply about these systems because of one thing: cost per kill. A single Patriot missile can cost $4 million. A Tamir interceptor, up to $100,000. A laser shot, around $1. In a world of cheap drones and mass-produced munitions, that economic advantage is not just attractive, it's essential. Lasers won't replace missiles, but they will ensure missiles are only fired when absolutely necessary. If this deep dive into the new laser arms race fired up your curiosity, make sure you tap like, hit subscribe, and turn on notifications so you never miss the next breakdown of future warfare and cutting-edge tech. Stay tuned, the future is charging up.